Now, let us finally take a look at an example of modeling. So, we will take a look at one of the simplest system that consists of the mass, spring, and damper. So, it's the simplest dynamical system. During the next lessons, we will take a look at how can you model a tour robot, for example, and finally we will be able to model robots with spatial dynamics. But now let us understand the basics. What is a model? What do you think a model? A model?
I think a model is the mathematical equations that define the motion or the behavior of the
Equation. It's the one which is called conceptual model, but actually a CAD model of your engine or STL file of a building that you want to print on your 3D printer is also a model. So model is actually something that represents the system of your interest. And the modeling is the act of creating this kind of model. During our course, by model, we will be thinking of an equation that describes the dynamics of a system. For example, here you can see an equation of open chain robot, which is fixed to the ground. So there is a mass of matrix, matrix of mass, Coriolis, gravity. We will take into this equation later. But here the main idea that by modeling we will going understand the act of deriving an equation of motion. All right, so model have to be simple, but still it has to represent the main characteristics of a system. It's like it has a different kind of characteristics, and sometimes it's not important to model all of them for your particular system. For example, here you can see a picture of a resistor. Let's assume that here I have a resistor. What kind of law should I use in order to model it? Ohm's law. But still, it's a resistor, it has its own mass, it has its own dimension, and I can throw it into you, right? And I can say that in order to do this kind of virtual experiment, I need second Newton's law, right? But still, it depends on your task. If you want to create the electric circus, you need the Ohm's law. For the resistance, it's pretty obvious that it's just stupid to model the mass and dimensions, right? But sometimes it's tricky when we talk about the complex systems. For example, you want to create the interaction of a robot with the environment. Do you need to describe interaction of each point of this robot, or maybe only of n effector? That depends on your task. If you model, create a model of entirely whole structure with environment, it will make your system much more complex, and it will be harder to model it for the computer. The simulation type will be increased like exponent in the power of factorial, and sometimes you not really need it. All right. So the good model is a judicious trade-off between realism and simplicity. Okay, so let's take a look at the way how do we model a system. So we're going to use a Lagrangian equation. It's called Euler Lagrangian equation. Do you remember? Can you raise a hand if you do remember the equation? Okay, not all of you, so I will explain you. So there was a guy, Lagrange, who derived the equation from the energy point of view. It's like we have a system, and if we derive the energy of the system, we can derive an equation that is going to explain us how it's going to behave, and we can use it to predict the future behavior. In order to model this system, we need to start with deriving a Lagrangian. A Lagrangian is the difference between kinetic and potential energy. So here, by K, I mean kinetic energy. And here, you can see mass, spring, and damper. Which one of these elements has kinetic energy? Mass, right. Only mass has kinetic energy, and it's 1/2 times mass times velocity in power 2. Minus potential energy. Which one, or maybe there's several elements that has potential energy. Which one? Mass and spring, yeah. We have potential energy for the mass and for the spring here. 1/2 times coefficient of stiffness K times deflection x in power of 2. All right. It is clear, right? For all of you. Great. Now, you can see here the way how a Lagrangian equation looks like. It's like we have in the left part full derivative, time derivative over partial derivative of Lagrangian in respect of velocity, x dot, minus partial derivative of Lagrangian in respect of position x. And if the system is isolated, those two components, the subtraction of these two components equal to 0. But here it's not isolated. We have a damper, and damper do not store any kind of energy. It just dissipate energy. So it is actually an external force which is applied to a body, and this is why we have a Q. And Q is external force which is acting on the system, and in our case it will be minus B times x dot. B is the damping coefficient, x dot is the velocity. So we know Lagrangian, we know the x is called generalized coordinate. Generalized coordinates, those are the coordinates, it's like diffused coordinates which can represent the state of a system. For example, for a robot that consists of 2 links, it has a lot of different kind of coordinates, for example, for all of the bodies, but the generalized coordinates will be the angle, the revolution angle for the one link and for another link. And we can restore all other coordinates if we know those. So x here is generalized coordinate. We can take the time derivatives, and we will get this data. So let's go back. If we want to take a time derivative in respect to x, we'll be left with a minus mg minus kx, right? So we have exactly that here. If we take a partial derivative in respect of x dot, we'll be left with just m times x dot, right? And if we need to take a time derivative, x dot will become x double dot, so it will be mass time acceleration. So now we can put everything in the equation, and we will be left with this kind of equation. It's called differential equation of motion, and actually it's model that will represent how our simple system behaves. Okay. Can you tell a lot about how the system behaves? Can you tell something about its performance if you have just symbolic expression?
We can actually.
what can you tell?
We can say that that the inertia, first of all, because we don't have an external force, if the system is stable, it will be stable forever.
It will be dissipate energy, and it will going to rest.
If it's in rest already, it will be in rest.
It's like here, x. It's not actually position; it's deflection here. So it's it's not in the rest position.
Okay.
It's okay.
Zero here is not the rest position.
Yeah. Or
second of all, the damper will split the force of inertia of this system. But actually, we can say that the behavior of the system depends only on the initial state of the system. We can say that. The trajectory or the path of the map will be, for example, a dissipating signal wave. But we don't know yet because we don't know the initial.
All right. So you already have some preliminaries, and I suppose that you already simulated some. Everyone. All right. Great. But the main point is when you have an equation, for example, for a robot, it's not something that you're going to use to say a lot about the final performance. We need numbers, not just symbolic expression. We need numbers, we need plots, we need figures, and maybe some criterions, but finally we need numerical representation. And in order to do this, we do simulation. Simulation, it is the way, is the process when we use just derived model in order to study behavior and performance in an actual or theoretical system. For example, here we can use this equation in order to plot these graphs. And it's already the presentation that actually it's going to the rest state after some period of time because of the damping coefficient. So in simulation, models can be used to study something that already exists or only a proposed proposed system. We can manipulate coefficients. So we will already discuss all these features. I would like to say something about optimization because we didn't put it here. It's like in simulation we can use some parameters, some numbers in order to simulate a system. For example, here it is a Chebyshev linkage, and we can do the simulation and calculate what is the difference between the desired behavior and actual behavior. And then you can use this error in order to create a cycle of optimization, such as you can tune the parameters, and finally you will have a system that completely satisfies you.
I have a question. Can I make optimization after build the model, or just when I make the simulation? It's good to make optimization after or before?
Optimization works with the numbers. It has rewards. It has constraints. It works on. It do not work with the symbolic expression. It works with the numbers, and you can use models within. You can put numbers there and work with the numbers finally. So you already will be using a model, so it's already simulation.
I have a question.
Yeah, sure.
Here, I think there's, I don't know if I'm right, there's two types of the optimizations, and I'm confused here. There's optimization that we use simulation to optimize, for example, the design for our task, or we use the difference between the behavior of the model of the simulation and behavior of the real life to optimize.
Yeah, it's different kind of optimization. Here it's in general. So here it's like in general we have some parameters. We take a look at the result and then we tune parameters in order
The
to.
model itself.
Here it's with the model, yeah, right. But still, this idea can be used to minimize the error between the model and the real life experiment. For example, if we want to find coefficients of interaction with environment, so when we're going to take a look at the contact modeling, we will see that you need to find some parameters. Those are not analytical, they like heuristics parameters, and you can find them out of a real life experiment. For example, you can feed the result of real experiment into your model, and this way you can tune the parameters in your model.
We can fix the model.
Yeah, you can feed your model with the results from real life experiment. Here, this slide showed us how can we use simulation and optimization in a loop, such as find parameters that gives us the result that we want in the simulation. Then we can check do have the same in the real life or not. So the blue one, when we do simulation and take a look at the error, it is something which is called direct design problem or direct design task. And the orange one is called inverse design problem when we use optimization techniques in order to tune parameters. So this we already discussed, so I'll just skip it. All right. So let us discuss this model. So we have derived the equation, and according to the second Newton's law, multiplication of mass with x double dot equal to the force, right? Let's assume that we do know force. Let's assume it. If we divide the force with m, what we will have? Acceleration, right? Well, if we integrate the acceleration, velocity, if we integrate it once again, position or deflection here. When we multiply the deflection with the coefficient of stiffness, yeah, we will compute the force which is generated in the spring. If we multiply the velocity with the damping coefficient, damping force. So, and if we'll add gravity, we'll have the force, and this is the way how we can just loop it. All right, and finally we can like assemble the equation in simulation packages such as MATLAB. So let us try it. So here I have a model. Let us take a look at here. Have you ever worked in MATLAB? Can you raise a hand if you're already familiar with MATLAB? Yeah. He has a black belt for the MATLAB. Okay, so here you can see the model that we just discussed, and it's pretty basic since it just consists of general Simulink blocks such as constant, gain, sum, integrator, and that's it. And you can actually assemble any kind of equation, differential equation like this, and you will get pretty useful results. Let's take a look at the results. So here, by the way, it's already an example of your first practice task. So you will need to do pretty much the same. All right, so here we have an x. We have an x derivative of x and derivative of derivative, so it's an acceleration, right? And we can play with the parameters. So here you can see a live script, and here I just wrote the derivation of equation. But after that, we can see the parameters. For example, I can put here 10 kilograms damping. We can make more stiffer spring. Let's run it. Not this one. And the result will be different. So you can see that the x, the velocity, and the acceleration now is different. It's pretty obvious, but still we can change the parameters, and we will see how it behaves differently. For example, if we use greater number for the damping, what we'll have? If we sure, let's check it. For example, instead of 1, I put here 10. Hmm? It will be the oscillation will like dissipate, and we can tune parameters in a way how we want. All right, but this system is pretty basic one, and for a complex system, for example, for a spatial robot, it's just a nightmare to derive such kind of equation. Especially if we want to model interaction, some complex control, we still can do this, but we also can take an advantage of modern simulation packages. And because of these reasons, MATLAB has not only general Simulink block, but also it has something which is called Simscape. Have you ever used Simscape? All right, some of you already used. And here, how do we create the simulation model using Simscape blocks? We just use iconic diagrams. For example, in our system we had mass, spring, and damper, right? And mechanical like frame. And here we have mass, we have damper and a spring, which is connected in parallel, and mechanical frame. Pretty much it. This is just a solver. We can connect it just in random position. It do not depends on where should we attach it. We just need to attach it. It is a sensor which measured velocity and position. And finally, it is an ideal force source to apply gravity. And if we'll do everything correctly, the results will be identical. For example, here you can see the results for the block diagram out of Simulink blocks and for the Simscape blocks, and the results coincide. And it is already much useful. The Simscape it allows you to model even more complex system with a multi-body, but we will consider it later. For now, we want to understand how does it work. For example, if you open a block, you will be able to tune parameters, but also you will see source code. And you can proceed, and you will see some variables, some code, but still, why do we use this code, and what does it mean? Why how does it work, and why we can just assemble icons and somehow it derives automatically the equation? And
Because if we didn't put that, it would be the ideal model.
what do you mean?
Because we must put anything related to the real world.
Yeah, sure, but my question about why the equation look in this way, and the only thing that we just assembled in according to a picture, and the whole derivation of equation was in automatic way. But how it's do this? And it will be the topic for the second lecture that we have today. And actually, we can see the bone growth method. It's one of the first methods that been created in order to automate the process of derivation of equations. It's been created in 50s at MIT.